Okay, so hello everyone. Welcome to the first meeting of the reading group at 2025. I hope this year we have lots of speakers, we have lots of meaningful contribution in the fields and lots of good things happen. So maybe before doing the announcement, I know that Mirko want to discuss something about conference. Mirko, if you want to.
Yeah, just very quickly, if I can share my screen, I can show you what
Let
we are
me,
doing there. Is it possible?
I think I could, right now you should be able to share your screen.
All right. So yeah, without wasting too much time, if you see my screen now, I would like to mention that we are organizing a kind of pretty big event, right, called IEEE MLSP. So some of you might already have known that. And this year will take place in Istanbul, in Turkey. And it's going to be in at the end of August, beginning of September. There will be 4 days of workshops, right? That's pretty good event and well known in the community. And I just wanted to invite you guys to consider submitting a papers. It will be a great event. And also the deadline for paper submissions will be on April 20, so 22. So please consider submitting a paper if you work in this field. That's it. So I shared the link in the chat. So again, you're welcome to contribute to these events. Thank you.
Thank you. So Haibin, I think now you could share your screen. Today we have Haibin Wu. He is going to present his work titled Neural Audio Codecs in the Era of Speech LMs. Haibin is a senior researcher at Microsoft focusing on speech processing. He completed his PhD at National Taiwan University, supervised by Professor Hang-Hee Lee. He is a recipient of the Google PhD Fellowship Award, and he has published more than 20 first author papers in top conferences. One of the main contributor for the S3 Perl open source toolkit, and also he co-organizes the Superb and Codec Superb challenges, helping set benchmark for speech SSL and codec-based models. So please welcome Haibin to the stage.
Thank you, Pony, for the introduction, and thank you for inviting me. I'm very happy to take this opportunity to share off some of my research in neural audio codecs, especially in this special timing when speech language models attract a lot of attention and achieve many developments. Neural audio codecs is usually consisted of three components: an encoder, a vector quantization module, and a decoder. As shown in the left figure, the encoder will comprise the time domain raw audio signal. Usually is 16K hertz to extract the frame-wise audio features to this is usually 50 hertz. And the vector quantization module will convert each frame-wise audio features into discrete tokens. And finally, the decoder will reconstruct the time domain audio signal from the discrete tokens. The neural audio codec is typically used for two purposes. Firstly, is audio compression, which compress the audio for transmission, storage, and playback. And the second one is that discrete audio tokens derived from the neural audio codec can be leveraged for downstream tasks such as speech recognition, speech generation, and the most interesting one, speech language modeling. And we know that language modeling has already proved successful in the NLP domain since the advent of ChatGPT, and speech contains more information than text. Speech not only contains the content information as text, but also contain other information such as speaker information, emotion information, acoustic event information. If we could apply the similar language modeling from NLP to speech processing, that would be promising. But there is one challenge. The speech signal is very long with 16K samples per second. Modeling such long sequence makes the LM training very hard and makes the inference very slow. And another thing is that WaveNet is a model, it's a very famous model for next token prediction or LM on the raw audio signals. So WaveNet can produce very high quality speech. The model doesn't learn a high level structure. Sometimes it will generate random babel. As shown in this talk from the author of MOSI, they share some of his thoughts of WaveNet and under the under the short backs of WaveNet. Okay, and then let's see. So we need one tool to help us do language modeling for speech. Codec is such kind of good toolkit. Codec can be leveraged to reduce the audio signal from 16K to 50 hertz, and Codec can also help extract tokens with structured information. And what's more, Codec can be leveraged to reconstruct the high quality audio from the discrete audio tokens. And let's see the speech language modeling procedure aided by Codec. Firstly, the speech encoder will extract the discrete tokens and discrete speech tokens, and these text tokens or speech tokens can be either can be both sent into the speech language models to generate the speech tokens. Finally, the speech token will be converted to the waveform by the speech codec decoder. This slide shows three overviews of speech language modeling. The left figure is a chat model overview. The middle figure is the multi-model next token prediction survey, and the right figure is a survey called Speech Tradent, which overviews the representation learning, or so-called SSL learning, and the neural audio codec together with the main branch speech language modeling. And we can see there is a milestone year, which is 2023. In 2023, we saw a lot of a great number of speech language models have been proposed. And in the meantime, a lot of neural audio codecs have been proposed, as shown in this timeline, starting from the pioneer work Soundstream in 2021, and there are a lot of codec models being proposed. Codec is our main topic today. This slide shows my research roadmap together with some open questions for neural audio codec. The paper highlighted in bold gray color are first author papers, and the papers with gray colors are co-author papers. Today I will cover three aspects of my research in Codec. The first aspect is the modeling, how to develop a neural audio codec for speech language modeling, which is also open and a very challenging question. Recently, there are a lot of promising properties for neural audio codec to aid the speech language modeling, such as low token rate, low computation, and even streaming. So how to develop a codec with such promising properties is very challenging. So TS3 codec is our first attempt to address this challenge. And the second part is the evaluation. Codec have gained a lot of developments since 2022, but by the end of 2023, there is still no unified, comprehensive benchmark to compare different codec models. So how to comprehensively evaluate codec models is also an open question in the end of 2023. So we proposed the Codec Superb, a benchmark, a unified benchmark to benchmark and evaluate the different codec models. And the third part is the security. Nowadays, the codec-based speech generation system can mimic any speaker's voice with human parity quality. This can be leveraged. This kind of systems, codec-based speech generation system, can be leveraged by malicious attackers for misuse, such as making fake news for famous figures or identity attacks. So to tackle these security issues, we introduce our solution, the Codec Fake and the Codec Fake Omni data sets. Okay, let's get into the first part, the modeling part. Which in this part I will talk about my recent paper, TS3 Codec. This is the paper title. TS3 Codec is a transformer-based streaming single codebook codec with very simple model design. One sentence to overview this paper is that this is the first attempt to develop a convolution-free and transformer-only neural audio codec. Let's recap the functionality of codec in speech language model. In the speech language modeling, codec serves as two functionalities. Firstly, it helps to listen to the speech, serve as the front end to encode the continuous speech into the discrete tokens, and also it speak out the response by the speech language models. So the codec is both front end and the back end for the speech language modeling. So in this paradigm, codec should have some good properties to support the speech LM. Property one is low computation, because in this paradigm, the main structure is the speech language model. So neural audio codec should enable fast encoding and decoding, and also reducing the computation cost and leaving more computational resource for the speech language models. And the property two is low token rate. We know that the that the speech language model is next token prediction is with the next token prediction task. So if the token sequence is too long, that will make the language modeling really hard. So it is preferable to use low token rate neural audio codec for speech language modeling. And the third property is streaming. Here, this figure shows a full duplex communication between the user and the machine. The user and the machine can speak simultaneously The full duplex communication for speech LM is still very popular and challenging in this domain. And in order to enable the speech language model both listen and speak in the same time with fast response, the codec should be streaming and then the codec can allow the audio be encoded very fast with very low latency. The last property probably is the single codebook. A single codebook based model is more preferable compared with the multiple codebook based model because the later one, the multiple codebook based speech language model, introduced additional complexity to the structure of speech language models. So a lot of decoding strategies have been proposed, such as the quartz for first and then fine-grained from the body, this token, this pattern, and the delay pattern from music gen, and the temporal and depth transformer from uni audio, but they introduce some complexity to the structure of speech language models and include some complex decoding strategy for the speech language model. For previous neural audio codec models, there are some limitations. Firstly, previous neural audio codecs with high token rate. For example, the discrete audio codec with 6K bps has 600 tokens per second, which can make the autoregressive language modeling very challenging and computational expensive. And the second limitation is that current codecs have very bad reconstruction quality at low bit rate, especially for lower bit rates such as 1 kbps. Current neural audio codec mostly operate on bitrate larger than 2 kbps. So in this work, we want to go even further to investigate codec under 1 kbps. And currently, there are less work exploring the streaming capacity of neural audio codec. And the second motivation is that in the neural audio codec, there is few research of transformers. In this timeline, most of the neural audio codec rely on the convolutional based backbone or convolutional dominated architecture. Only with a few models try to include the transformer as intermediate layer within the CNN-based architecture. For example, the wave tokenizer include the self-attention to boost the feature engineering. The MIMI also include the transformer in the middle of the CNN-based backbone. So there is one open question that the performance of purely transformer-based and convolutional free architecture in neural audio codec remains unexplored. So we proposed the TS3 codec, which is a transformer-only codec. This figure shows the entire workflow of TS3 codec. Firstly, it includes the WaveNext front and the backends. WaveNext is a vocoder with excellent performance, and it also performs better than the vocals, which is also a very excellent vocoder. So we choose the waveNext as the front and backend architecture. And let's see in this figure, the front end is two linear layer. The waveform will undergo the reshaping to get the tensor of shape f by n. N is the frame size, and f is the sequence length within one frame. And this feature will go into two linear layer, one without bias and another one with bias to get the features. For the backend, the backend is an inverse of the front end. The backend will include one linear perception with bias and another linear perception without bias to convert the speech features into a folded speech waveform, and this one will be reshaped to the time domain signal. And the second property of the architecture is that this TS3 codec is transformer-only architecture. We choose transformer because of two reasons. Firstly, the transformer under the same parameter setting, transformers have much less parameters compared with CNN-based architecture. Here is one example. If we use for big codec, which is the convolution-based codec, if the big codec parameter is 160 million, the computation is 660 max, and for transformer, if the transformer have 60 max, the parameter will be around 1.6 billion. So that means for convolution, for convolution, 100 million parameter convolution layers have similar computation with a transformer with 1 billion parameters. And the reason to choose transformer is that transformer offers simplicity in model design. For transformer, we only need to change the maybe layer number, how many layer we choose, the hidden dimensions. But for convolution, we have to carefully design the downsampling and upsampling strategies. And the transformer main block is shown in both in the encoder and the decoder. For these transformers, we use the self-attention with left fixed window. So with left window, because we use left window because we want the model to be streaming. We use the fixed window because we want the model we want the computation not proportional to the quadratic of time. And for the vector quantization layer, we do the linear projection to project the features into low dimensional for vector quantization in order to enlarge the code book usage. This trick has been proposed in previous paper. And the last thing is that we are the first to enlarge the codebook size to 65K and 130K. This slide summarize why we choose transformer rather than convolution-based architecture. Convolution is well known for its parameter efficiency and reusability, but on the other hand, this reusability means that for similar parameter size, CNN typically require significantly more computation than transformers. And secondly, convolutions have inherent bias for different feature map in different time stamps. Convolutions apply fixed weighted sum weights across all the feature map. These weighted sum weights are fixed for all the time step features, but for transformer dynamically decide the weighted sum weights by the self-attention corresponding to the input features. And the third one is that transformer offer simplicity in model design. CNNs require careful tuning of kernels and downsampling mechanism due to their inherent bias. If you have tried training or designing the codec architecture, the up and downsampling strategy is very important. If you haven't chosen one good up and downsampling strategy, the model even cannot converge or converge to some suboptimal point. Okay, let's get into the experiments. In this paper, we have 6 baselines. The first one is in Codec, which is a pioneer codec, and also we choose DAC, speech tokenizer, MIMI. These 2 codec are with semantic distillation, which can make the discrete codes semantic rich. And the last 2 are single codebook codecs. In this column, the SEM means the semantic distillation. These 2 codec has semantic distillation. This column means the streaming. Encodec and MIMI are streaming codecs. And this column shows the VQ type. The first 4 codecs are residual vector quantization. The last 2 are single codebook vector quantization. And this column shows the architecture. We can see most of the codec are convolution based architecture with LSTM in the middle layer. These 2 models include the transformer or self-attention in the middle to boost the feature engineering. This figure shows this table shows the performance of different codec under 1000 bps. We show different properties of the model, whether the model is streaming or not, the bitrate, the codebook layer, the frame rate. The frame rate is how many frames per second. The token rate, which is how many tokens per second. And we also show the complexity with 2 metrics, the max and the parameter number. We evaluate the intelligibility with the word error rate and the story, and the distortion evaluated by the PAS and MCD, the speaker similarity, and the naturalness. So firstly, we want let's say the first 4 rows. These 4 baselines are non-streaming baselines. We can see that big codec outperforms other models with a large margin. For example, for word error rate, big codec is only 2.8 word error rate, but others is significantly higher than big codec. And what's more, for the UT models, we can see the bit codec is 4.11. The ground truth UTMOS is only 4.09. So bit codec has very good naturalness in speech quality. Thus, we choose the bit codec as our baseline to change the bit codec to the streaming version to compare it with our proposed model. And in order to make the bit codec streaming version a strong baseline, we do a lot of hyperparameter training. If you directly train the bit codec to streaming version, the performance is really bad, which make it not a very good baseline for us. So we do a lot of hyperparameter tuning to make this bit codec a strong baseline. And note that another finding is that wave tokenizer also has some very good UTMOS as highlighted in their paper. I see one question. Oh, it's not a question. Oh, so wave tokenizer has very good naturalness as highlighted in their paper, but the word error rate is worse than other baselines. Then we compare models under the streaming setting. We can see the numbers highlighted in gray background are the best performance. So we see that TS3 codec model performs the best for STOI, task, MCD, and the UTMOS, and the second best for word error rate and speaker similarity. And note that the Mimi model has very good word error rate, probably because their inclusion of semantic distillation. We also consider including such semantic distillation in our model in the future. And this table shows the performance for 600 bps. We can see that TS3 codec achieves the best performance under this matrix, and the second best performance for the word error rate. And also we can see that the TS3 codec compared with the two non-causal model, it performs better than the two non-causal models for a large margin. Another finding is that the speech tokenizer performs very bad in all other metrics except the word error rate. And we listen to the audio samples from speech tokenizer. We found that the generated audio sounds like female robotic speech, but the content information is right. So this shows the power of semantic distillation, which can inject the semantic information into the discrete code from the audio codec. Then we compare the TS3 codec with the bit codec. This 6 figure shows the performance versus the computation. The x-axis is the computation, y-axis is the performance. And then in order to get better visualization, we inverse the word error rate, inverse the y-axis of word error rate and the MCD to make sure all the points located in the left upper corner represents the best performance with the least computation. I see one question. Are there any plan to release TS3 codec checkpoint? Actually, there is some logistic issues to release the model. So currently we don't have plan to release the model. But if you have any questions, you can regarding the implementation, you can email me. And I think the current paper some of my friends is trying to reproduce the model. Probably in the future, they will release some GitHub repo. I will share it. Yeah, and in this figure, we also show the bit rate. The cold color ones are the big codec. The warm color ones are the TS3 codec. We can see that under similar computation budget, the TS3 codecs always outperform big codec significantly across all the metrics. And the TS3 codec, in order to achieve similar computation, similar performance, TS3 codec achieves TS3 codec requires less computation than the big codec. Maybe take this model as an example. In order for this model, this big codec, it requires 40 giga max, and for this TS3 codec, it requires only 6 giga max, and but the TS3 codec performance is already better than the big codec. Okay, this is a summary of the TS3 codec. TS3 codec attains a lot of good property. For example, the streaming, which can support the full duplex speech language modeling, and the low computation, which can save computation for speech LMs, and the single codebook design, which can avoid complicated speech language model decoding structures, and the low token rate or bit rate, which is good for the speech language model training. Okay, let's get into the second topic of this talk, the evaluation. We propose the Codec Superb, which is the first benchmark to evaluate codec models from both signal and application level perspectives. As shown in this figure, there are a lot of codec models being proposed for transmission or codec-based speech language modeling. But by the time of the end of 2023, there is no unified benchmark or evaluation toolkit to compare different codecs. Another motivation is for previous works, only signal level evaluation is conducted for codecs in previous works. But signal level evaluation is not enough to evaluate the information preservation of codec models. So we need application level evaluation. So we propose the Codec Superb. The framework is shown in this figure. The input speech will undergo the encoder to get a code, and the code will be sent into the decoder to get the resynthesized audio. The resynthesized audio will be evaluated under two evaluation perspectives: the signal level evaluation, including these five main metrics for speech, audio, and music, And the application level evaluation, we use ASR to evaluate the content, speaker verification to evaluate the speaker, and the emotion recognition to evaluate the paralinguistic information, audio event classification to evaluate the audio information. And also we propose an overall score for better visualization of the results, only using one score to show the performance of codec models. And we show that the overall score has a strong correlation with the signal level metrics. Here are some of the results back to 2023 on application level evaluations. We show for applications, the x-axis is the bit rate, y-axis is the performance corresponding to different applications. And the right line is the encodec, which serves as the baseline. We can see back to 2023, under low bit rate, the codec B, academic codec, is preferable, and under mid bit rate, the codec D, DAC, is preferable. And then nowadays we have a lot of some of new codec benchmarks. For example, the DASP proposed by the host of this talk, Pony, and the DSP extracts the codec discrete codes for discrete representation learning. Specifically, they use the discrete code to train ASR model or speech synthesis model to evaluate the quality of the codec codes. And another benchmark is the ESP-NET codec. They unify the codec training setting, including the training data, the training recipe, hyperparameter for various codec models to compare their performance. I think I'm running out of time, so I will quickly talk about my third aspect, the security. Recent codec-based speech synthesis model can mimic any speaker's voice with only maybe a 3-second segment of that specific speaker. This kind of technology can be leveraged by some malicious attackers to do some misuse. So how to mitigate the deepfake attacks from the codec-based speech synthesis models is a very challenging topic. So in order to counter the deepfake attacks, we propose the codec fake and the codec fake omni data. This is the paper title. To overview this paper in one sentence is that this is the first anti-spoofing dataset to counter codec-based speech synthesis deepfake attacks. The codec-based speech synthesis models is usually neural codec-based speech language models such as Valley, SpeechX. The input will be the context including the content to be generated or the text instruction, such as happy or maybe sad voice, and the speech encoder will encode the speaker prompt to the discrete codes, and these two codes will be sent into the neural audio codec based language model to get the speech codes corresponding to the specific speaker and the specific content. Finally, this code will be sent into the decoder to get the really high quality speech. And as I mentioned, this system can mimic anyone's voice with only 3 seconds of audio, and the generated audio is with very high quality. And then there will be one question: can previous anti-spoofing models counter such attacks? We do the experiments. We use the state-of-the-art anti-spoofing model, and we use the mainstream anti-spoofing data set. Usually, combining these two can result less than 2% equal error rate for traditional to counter traditional TTS attacks. But for the codec-based speech generation system such as Valley-X and SpeechX, we show the performance here. We can see the equal error rate is higher, is far more higher than 2%. So we propose our solution to train on speech resynthesis the data by codecs. Let's see this figure. The codec is the final step of the codec-based TTS systems. So we assume that the codec resynthesis data shares some similarity with the codec fake data, which is generated by the codec-based TTS system. So based on the assumption, we gather codec resynthesis data to train the anti-spoofing models. The dataset creation, we use the VCTK as the source dataset, and we divide it into 3 parts: training, validation, and testing, and resynthesis them with different codec models. For the codec models, we have 6 types, 6 frameworks, and with different training configurations, resulting in 15 audio codec models. For the source speech from the VCTK corpus, we do the resynthesis and to get such fake speech and gather them together, the real and fake speech, into the specific codec subset, and we use such subset to train the anti-spoofing model. We assume that based on the training of resynthesis speech, the model can somehow detect the codec-based resynthesis, can somehow detect the codec fake speech generated by such systems. This is the detection performance. The y-axis is the equal error rate. The lower, the better, and the x-axis is the training data for it's different training data. We can see for the traditional data set, the equal error rate is 14%, and the other 3 codec resynthesis data sets can result in better performance than the original data set. And for encodec, it can reach 0.4 equal error rate. We have proved for when using the traditional anti-spoofing data to train the anti-spoofing model, the model cannot detect the codec-based speech synthesis system generated data. And when using the codec resynthesis data to train the model can detect the codec fake speech. The next step will be source tracing. Source tracing offers because source tracing offers potential to improve the generalizability to spoofing attacks that are unseen during training, but are composed of blocks encountered in training. For example, for FA codec, it has some properties such as disentangle. If we use such codec to train the anti-spoofing model, when the anti-spoofing model encounter some disentangle-based codec fake speech, it can also detect that kind of speech um, and give the right prediction. This is a summary with papers for this talk. For evaluation, we propose the first neural audio codec-based benchmark. For modeling, we propose the first transformer-only codec. And for security, we propose the first codec fake dataset. This is the last page of this talk. This figure shows an overview called speech tradent. We gather three kind of models: representation learning, also called SSL learning, and the neural audio codec, and the main branch speech language model. We gather papers for the three topics in this repo. And we will also organize some special sessions, tutorials in speech conference, and release the video and the slides in this repo. For example, for Codec Superb SLT 2024 special session, we invited 5 speakers, including the author of MOSI, the author of Uni Audio, and the author of VoiceCraft, and so on, to give talks. And we release the slides and the recording in this page. If you are interested in the speech language modeling or neural audio codec, you can follow this repo. Yeah, that's all I have today.
Thank you, Haibin, for the presentation. If anyone has any questions, please drop them in the chat or raise your hand so you can talk to Haibin directly. Joshua? Yeah, you can ask your question.
Yeah. Can you hear me okay?
Yes.
Okay. First, thanks for the very thorough talk. I very much enjoyed this. My question is, in this talk, there's a few phrases that are used. There's the speech codec, sound codec, audio codec. I imagine that models that are trained on speech versus models that are trained on music versus models that are trained on just everything learn different representations. Do you know anything about this? I don't. So I'm wondering if people have looked into this and if that's something that has implications.
You mentioned that codec trained on different types of data will attain different properties. Yeah, the answer is yes. They for actually, I'm mainly focusing on the speech codec, and some paper are talking about music and audio codec. They are with different properties. For example, in this page, the author of semantic codec from by Professor Wen Wang, he shared a lot of insights about the codec for audio. They proposed one very good codec for audio. Yeah.
A little follow-up. I'm thinking that there's, in terms of data in the world, it's a lot harder to get clean speech. It's hardest to get clean speech. It's a little bit easier to get dirty, noisy speech. And then after that, just audio, it's easier to get random audio. Um, have have you looked at training models that are for general audio, or has anybody, because I'm not familiar, looked at models, codecs for trained on general audio that are then used for speech?
Oh, I think probably in this paper, maybe they have such experiments. Yeah, I think they also evaluate something on trend on audio to evaluate on speech. Maybe I'm wrong. Yeah,
Okay, I'll take a look though. Thank you.
you're welcome.
Thank you. So there is a question in the chat. So someone said, thanks for the talk. In part 2, when there was a comparison of audio codecs, were the hyperparameters selected optimally for every codec or they stayed the same?
Let me see the question.
Sure.
It seems the temporal compression only happens during audio patching. You mean the input part, right? The input front end?
Yeah, the input front end.
Yeah. What are the motivation? The motivation is that we probably want to we only want the downsampling happens during the front end to make the model simple. And the other question is how would you downsample purely with transformers if we don't want to be too aggressive during audio patching? Secondly, given its low frame rate and flat code, has the codec been evaluated by applications such as TTS and demonstrate good performance? Yeah, thanks for the two very good questions. Probably for the current patching, for the current patching, it is maybe 400 points for each patch, and we and I think it's not so aggressively downsampling, but we can try to incorporate the more maybe linear layer or convolution layer to make the downsample more smooth. Um, Based on the current results, the patching is not aggressive because we get very good performance. And we can try this maybe this trick to smoothly get more fine-grained do downsampling with the convolution. And secondly, do I train the TTS with this model? Actually, we train such model, but I think I cannot disclose some results in this stage. Yeah.
Got it. Thank you.
Okay, so someone asked something before. They said in part 2, can you see the question? Ivan, when there was a comparison of audio codecs?
What are the plans for updating the leaderboard? There are a few new models, and if you are planning to, you are open to new contributions, I'd be happy to participate. Oh, thanks for the question. Actually, we are recently have a new evaluation plan. Maybe I will chat. I will paste the paper here. Actually, this work is collaborated with Shinji's lab from CMU. They propose a very good uh, evaluation toolkit called Versa. And in this Versa, we get some we provide some script to evaluate the newly released codec. And if you are interested to contribute something, you can contact me by email. We can see there if there are something we can collaborate. You can look at this paper. I pasted it in the chat. And another question from Evan. In part two, there was a comparison of audio codecs or the hyperparameter selected optimally for every codec, or they stayed the same. You mean the codec superb benchmark? Yeah, for this benchmark, we for each codec, if they support different bit rates, we uh we will evaluate all the bit rates they support to report the results.
Okay, Mirko has a question.
Yeah. So thank you, Haibin, for the great talk. I have a general question. So many people, including with your work, are trying to make codecs as efficient as possible. But considering that we are gonna use our codecs in LLMs, right, in a very big model, how much is really important to make that efficient? Because you still most of the computations will be still taken by the LLM model, right?
Yes, yes. For yeah, it depends. I think if we put the model in the cloud, or there are a lot of maybe computation resource, the computation of codec is can be omitted. But if we put it in some smart glasses or some on-device device, so the computation of any module will be counted, right? Even for I think I did one internship in Meta React Lab. They did some research or development for the eyeglass smart glasses. They care about every computation, So depends, yeah.
So you envision a model where like the encoder, the speech encoder and the coder are done locally, and instead remotely on a cloud only the LLM parts, right? That's my understanding.
Yeah. I envision that will be one thing, and because for this is one thing you mentioned. It's a very good point. I think for the code, for the code in transfer or transferring the code, transmission the code rather than the audio itself, it will avoid some security issue. This is one thing. And another thing is that I envision maybe in the future we will have some on-device LM, speech LM.
Okay.
Yeah.
Yeah. There's a big trend also in Europe. There were many works on that. Yeah.
Oh,
So I have one curiosity for you. So if you go back to slide 23,
23.
so where you have the architecture of your TS3 model.
TS3
Yeah.
model. Yeah, okay. Here.
Yes. So what's the reason why having two consecutive linear layers here, one with bias, one without bias, but in the end you will have still a linear transformation, right?
Oh, yeah. This is also a very good question. Actually, I just follow this paper. Because they have seen they have used two linear layers, so I just choose to use these two linear layers without any modification. Yeah.
I feel you can make that more efficient, right, at inference time by even without retraining. You can like just combine the linear transformation into a single linear transformation and make your model even more efficient, right? Potentially.
Yeah. This is a very good point. I'm also thinking about it when I write the paper. When I write the paper, I start to think about maybe I can use one linear layer instead of two, because these two are similar, are equivalent to one linear layer. Yeah.
Okay, thank you very much, Haibin. Great job.
Thank you.
Thank you. I think Pune has something to say.
And is the slide. I want to ask, like, I have seen that you enlarged the codebook size to 65. So what is the metric to decide what would be the correct codebook size to choose here? Like, in order to make sure that all of the codebooks are using and also they could include diverse information.
Oh, actually, this is a very good question. Enlarging the codebook size will reduce the codebook utilization. And in order to choose a good codebook size, we just try some ablation study to increase the codebook size to see which one is better and which one can also maintain the codebook utilization and also good reconstruction quality. Yeah. And why I do not increase this codebook even further, because currently for some language models they only support maybe 200K or 300K. We don't want to push it even larger. Yeah.
Yes. Thank you. I think we cover all the questions. Yeah, Eva?
Yes,
Yeah.
I think we don't have any more questions.
Perfect. Thank you, Haibin. That's a really great talk.
Thank you.
So next week, we have Martin Bartels. He's a postdoc at Stanford University, advised by Professor Dan Durofsky. He's presenting his work titled Improving Universal Access to Modern Speech Technology. The event is open to public, so please share with your friend, your network, and looking forward to see all of you next week. Thank you all.